On our quest to understand all there is to know from a graph, we're going to be looking next at symmetry. Now there's three specific types of symmetry we're going to look for from a graph: y-axis symmetry, x-axis symmetry, and origin symmetry. Now y-axis symmetry means that if you were to take a graph and fold it on the y-axis, two matching sides would be the same. So for example, this graph has y-axis symmetry. X-axis means if you fold, let me come back here for a second. So the y-axis goes right down the middle of the graph. X-axis symmetry means if you were to take a graph and fold it along the x-axis, both sides would match. So how about a graph like this? This time, if you were to fold it right along the x-axis, the top and the bottom would match. Now the third one is origin. Origin's a little funny because that's just a point, and you can't fold on a point. But a graph with the origin symmetry would be one like this. Now I see here a rotational symmetry. If you pick up one piece and rotate it around 180 degrees, it would land here. Another way to think of it as two reflections. Take a bottom portion, rotate it over the x-axis and over the y-axis, and then they match up. Now our goal here isn't actually to be able to tell just by looking at the graph what kind of symmetry it has. Instead, we want to be able to find this information through looking at the equation. So to help us get there, imagine that this point on the graph is the point 1, 2. Now let's put some paint on that point, fold our paper over on the y-axis, open it back up again. Where did it leave its mark? Well, its reflection is here at the point -1, 2. Let's try the same thing here. If this is the point -1, 2, we fold it over, it would leave its mark here at -1, -2. And finally here, this is the point 1, -2. If you put some paint here, you reflect it over the x-axis and then reflect it over the y-axis, that would end up at the point -1, +2. So look at how those numbers change in each situation. In the y-axis symmetry, the y value stays the same, but it's the x that gets reflected, and both +1 and -1 are on the graph. So if you have a graph with y-axis symmetry and the point xy is on the graph, then so is -xy. For x-axis symmetry, the x value stayed the same, but it's the y value that became the opposite. So if xy is on the graph, so is x -y. And finally, for origin symmetry, both the x and the y became the opposite. So if xy is on the graph, so is -x, -y. Now this plays a key role in how we tell if the equation is going to have a certain type of symmetry after we graph it. So for this one, since both of these are on the graph, what we're going to do to the equation is replace x with -x. You're going to simplify it, and if the equation is the exact same one that you started with, you know that that graph will have y-axis symmetry. For x-axis symmetry, we will replace the y with -y. See if you get the same thing. And finally, for origin symmetry, we're going to replace both the x and the y with their opposites. And then check to see if what we end up with is the same as the original. Let's try an example. Y equals x cubed. Determine if the equation has any type of symmetry. So first, let's check for y-axis symmetry. Now, as you do this, I want you to show your work, even if you remember what this graph looks like and understand what kind of symmetry it has. Let's practice the algebra here. So for y-axis symmetry, we replace x with negative x. So we have y equals negative x cubed. Now to simplify this, we would do a negative x, and negative x. X times x times x, that's still x cubed. A negative times a negative is a positive, times a negative is a negative. When we look, is that the same as our original? No. Next up, let's check our x-axis symmetry. So we replace y with negative y. There's nothing to simplify this time, so is that the same as our original? No. Finally, we get to origin symmetry. That's where we have to replace both. So we get negative y equals negative x cubed, which is not the same as what we started with, but if you notice, both sides are the opposite. So we could use algebra, divide both sides by negative 1, and we have a negative divided by a negative gives us a positive y. A negative divided by a negative gives us a positive x cubed, and this is actually the same equation we started with. So yes, the graph of this function will have origin symmetry. And just to give you a picture, y equals x cubed looks something like this. And again, this is just a sketch. There's the graph of y equals x cubed. The origin is right there. So we could take 1/2 of this graph, rotate it around, and end up with the other side. Push pause, work out B and C, check what kind of symmetry it has, and come back. Okay, I've already worked these out here. So B, we should have that this graph has y-axis symmetry. Make sure that we have our negative x squared, so a negative times a negative gives us positive x squared. The graph is a parabola. The y-axis splits it right down the middle, so there's the y-axis symmetry. For C, make sure you follow order of operations when you simplify under the x-axis symmetry. You have to apply the exponent before you multiply. So negative times a negative turns this into a positive y squared, and then that minus is still there. So this graph has x-axis symmetry. It's a sideways parabola. X-axis splits it down the middle, so this graph has x-axis symmetry. Next up, we're going to talk about something that is very closely related with symmetry, and that is even or odd. Now, when we talk about symmetry, we're specifically talking about the graph. We could say that a graph has origin symmetry, y-axis or x-axis symmetry, but we wouldn't properly say that the equation has symmetry. Instead, if a graph has origin symmetry, we say that the equation is odd. If a graph has y-axis symmetry, we say that the equation is even. And if a graph happens to have x-axis symmetry, well, that equation gets left out. It does not get a special name. These are the only two that have a special name. Now the reason origin is called odd, because look at this exponent here, x cubed. That's our most basic odd function. Same way the reason y-axis symmetry is even, because our parabola x squared is our most basic even function. Let's fill these in here. So a function is even if it is symmetric with respect to the y-axis. A function is odd if it is symmetric with respect to the origin. Well, there's another good way to remember, O and O always go together. And a function is neither if it is not symmetric with respect to the y-axis nor the origin. So now, when we want to check a function, we only need to check y-axis and origin symmetry. So we're going to check this the same way we just did. Here, you would replace your x with a negative x and see if you come up with the same thing. If this is the same as this, then we would call the equation even. Otherwise, we check for origin symmetry. Remember, that's where you replace both the x and the y. Compare this one to this one, and if they are the same, then it is an odd function. Now this one, as you work it out, it's not the same, but every piece is the opposite. So if you divide by -1, if you divide by -1, this is the same function we started out with, so we would say that this function is an odd function. Try out B, and then come back. Okay, first, I want to check for our two types of symmetry. So here we would get negative times a negative, so we would get positive x squared plus 1. That is the same as our original, so we know that this is going to be an even function. Now, a function can never be both even and odd, but just for practice, let's check it. Also, if you check it and you get yes for both of them, you know you made a mistake somewhere and you need to go back and check your work. So here we get negative y equals x squared plus 1, not the same, so that's an even function.